So welcome back to this small session on cross-validation and resampling methods. So last week, we discussed the bootstrap method as one way to resample the data, and where the overarching goal is actually to get a, hopefully, better estimate of the variation in expectation values like the mean squared error. Now, the bootstrap method is a method which has been widely popular on small data sets. However, the bootstrap often means that you resample your data set many, many times. And sometimes this can lead to a bigger computational expense. So the method, which is a kind of a preferred method in machine learning, is this method which is called cross-validation. This method is actually simple to implement, but you can use the functionality which we have in scikit-learn here. So you don't need to write your own code for cross-validation. So let me try to explain briefly what this actually means for us and what kind of results you can expect and why we do it. So you will find in the lecture notes for this week, if you scroll down till the end and you look at the lab session from for this week, and that contains also some material from last week, which we didn't get the time to cover. So just take a look at this material on resampling methods. And now we're going to dive into the cross-validation. So let me try to explain in some simple words what it actually means. So I'm going to switch to the whiteboard, and we are going to look at the first one method which people have been using, but which is less used in the scientific applications of machine learning methods. And one of these methods is called the holdout method. So what we want to do now, so we want obviously to have a good estimate of the training parameters, which are the betas in linear regression, or logistic regression as we discussed yesterday. But the other thing we want to do is to tune the hyperparameters, because in essentially all of the machine learning applications, we are going to have additional parameters. And to many, this is a kind of disappointment. Actually, this k-fold cross-validation introduces a new parameter, the number of folds which we are going to make. And the results will depend on that. So that's an additional parameter. And this week, we introduced during the lectures, we introduced the so-called learning rate, which is a new parameter. And when we next week, we discuss gradient descent methods like stochastic gradient descent, there's going to be 2 more new parameters. And this is just going to pile up. And some people get disappointed because they ask themselves, I mean, how can I get something meaningful out of this jungle of parameters? Yeah. So the hyperparameter lambda is one of the important parameters because you add terms to the functions you want to optimize. And we've been discussing that in connection with ridge and lasso regression. So to tune them is a big question. I mean, how do we actually tune them? Can we do this in a, how to say, a scientifically meaningful way? So the holdout method, which is not that much used, is a method where you would take the data set and then you would split it in train and test, as you've been doing before. But then the next step is to split this in a train and validation set. So suppose now that you split the test train in 80% train and 20% test. Then you take this 80% and you split that one in a smaller training set, which could be 60%. And then you use 20% of this data to validate your model. So what does validation mean? So in the training test, you run many experiments with different hyperparameters. On the validation part, you find the optimal hyperparameter. With that, you have trained what you think is the best model. And when you do this, then you would then apply it finally to the test data, which has been untouched by you and the model. Now, in this case, the train part would be you applying the algorithm, which you have developed. You perform a fit, as you can see here. You can then change the hyperparameter, as you can see from the drawing here. And that will be part of the training as well. So you would change the hyperparameter lambda, then you evaluate and you find the parameter which is the best one, and that gives you a predictive model which you then would at the end apply on the test data. Now, this is a method which is not much used anymore. Now, what is common to do is to use this k-fold cross-validation. So let me try to explain what that actually means. It's pretty simple. It's basically even simpler than the bootstrap method. This is a method without replacement. So in the bootstrap, we had with replacement, which means that we could get the same data entry twice or more. Now, in the k-fold cross-validation, what you would do then is to take your data set. Now, you can do several things here. And we are coming back to what kind of recipes people normally follow. So what you could say, take the whole data set, and then you split the data set into 5 different boxes. So you do the splitting randomly, so your data gets shuffled around. This is also pretty common when you implement the train test split from scikit-learn. That reshuffles your data from the original order which you had. So every time you run a train test split and you don't reset it with the same random numbers, you may actually get slightly different results. Now here, you shuffle the data randomly, and then you define, in this case, 5 slots or folds, as they're called, which means that you have these 4 firsts are used in the training. So you train the models. So the idea here is that you're taking your data set, and in order to avoid overtraining a specific data set, you now shift the data you train on. And that means that you apply the model which you have trained on this test data, which was not included. And then you calculate a mean squared error for the test. Next, you repeat this exercise. So with 5 folds, it means that you will have 5 test data sets. So you've done the random splitting first, and this is now your new data. And this is split into 5 different slots. So scikit-learn has a function which does all this for you. That means it finds where this starts and ends, where the next one starts and ends, where the test data starts and ends. So it picks the right indices for you and sets up the training data and the test data. And then you perform a new training with these data points here. So hopefully by doing this, you have different data sets in each case and different test cases. And then you produce a mean squared error for the test. And then you repeat this 5 times because you have 5 folds. That means that the mean squared error you produce is the average of these 5 training cases. Now, this k-fold, or this variable k as we called it, is a variable you have to play around with. So this becomes a new parameter for us. And if you go into the literature, you will see that a kind of magic number is roughly 10. But if you have much data, you can actually decrease this to 5. But if you have few data, there is a method which is called leave one out cross-validation. So if you have 1,000 data points, every time you do this k-fold, you just take out 1 point for testing. So that means you would do 1,000 trainings applied to one data point. And so instead of 5 folds here, if you have 1,000 data points, you leave one out. This is something you would often do if you have little data. It's not so much used because it means that you have to do this many times. And every time you train, if you have a heavy model, this is going to take a lot of time. So doing this k equal 5 to 10 is going to be a compromise between the number of CPU cycles you're willing to spend and the quality of the results you want. So it's you who at the end has to strike this balance. So when you're dealing with the models like ridge regression or lasso in project 1, this is a kind of analysis you need to do when you're finding the best hyperparameter lambda. Now, what does this mean for us? Because if I do this 5 times, I will get 5 different betas, right? So which beta should I pick then? Should I take the average of these 5s? Actually, this is not the way we proceed. So you do this training to find the best hyperparameters. You nail that down, and then you do a new training with that specific value. And then you apply that to a test data which was unseen. Okay? So it's a recipe which is very much used to find the optimal hyperparameters. So let me show you some examples of codes which you will end up using and how you can use this in connection with the project. So one thing which you will also have noticed is that doing the bias variance trade-off on this is a little bit more tricky because we are changing the test data continuously. Whereas when we did the bias variance trade-off, we just had one test set which was just kept as it was. So you can think of this cross-validation as a way to fine-tune some specific parameters. And then you do a new final training. And there you can take your data again and do a train test split. Or if you look at the vanilla data we are dealing with in project 1, this Franke function or whatever, you can actually just produce new data immediately on the fly because it's so cheap. But normally that's never the case. So in a way, we get a little bit spoiled when we deal with the projects because we have a feeling that I can just generate data quickly, but that's not the case, sadly. And to gain some data, to get some data can actually take many, many years. But let's look at one of the examples and in the slides or the Jupyter notebook, because that gives us a kind of a feeling of what you may expect in project 1. So this just repeats this basics of the cross-validation. So the algorithm is very easy to write yourself. And it's just you reshuffling the data and finding the indices after you decided how many folds you want to have. And the best way to look at is actually at this Python code. So in this case, I have 100 data points. I have one of these vanilla functions again, x squared, plus some random noise. And now I'm making something less intelligent. I always do that. That's at least my wife and my daughter always agree with me on that. And I now want to fit a polynomial of degree 6. Okay. So, and then I do an exceeding large number of lambdas. I put 500, which you would never do typically because your algorithm may be very time consuming. When we're dealing with neural networks, 500 lambda values is a luxury. But then what I did here was a mix of first using scikit-learn and my own code for the cross-validation. So you can see the basic steps. So I got a little bit lazy. So I took this function k-folds. So I decided I want to have 5 data sets of the 100. So each one contains 20 points. Now, what this function does is that it sets up the indices, start and end of each fold. So it gives me these indices. So I reshuffle my data and it tells that box 2 or fold 2 starts from point 21 and ends at point 14, for instance. So it does the reshuffling and finds the indices. And as you can see here, I'm now running over the lambdas. I'm doing a ridge regression. And I now start with the training indices and the test indices. And these are given by this k-fold split, which I used, this function which I have from scikit-learn. So if you want to, you can actually write your own functions for it. But this saves you a lot of time. And actually, the recommendation which we give here is that you use the cross-validation score function which scikit-learn has. That makes life much easier. So here, I now do the training. I have my polynomial fit, which I want to do. I take the training data. I perform the ridge fit with it. I get my prediction here with the predict function. And as you see here, I compute now the score for each fold. So for each test case, I perform now a calculation of the score. And as you can see here, this is on the test data, which I have. And I compute the mean squared error, which is this quantity, as you can see here. And that's on the test data. So every time, for every fold, every training which I do, in this case, I have 5 training occasions and 5 test cases, which are different all. And then I can calculate at the end a estimated mean squared error by taking the mean of all these mean squared errors. And the hope then is that this mean is a better representation than the individual ones from the different training sets which I had. So typically this number k-fold ranges from 5 to 10. These are typical values which are being used. And you need to play around a little bit. If you have little data, you would often increase k. If you have huge data sets, it's common to have a number closer to 5. But this is something you need to explore when you do the training. Now, this is a kind of a hybrid part of the code where I use this split setup by scikit-learn, which is this function split here. But then you can use, if you want to, you can simply use the function which is called cross-val score. And in this case, you plug in your method, ridge here, which we have defined here. And you give the x and the y data. You define the score function. And in this case, you also need to define the number of folds. So this is a function which is pretty easy to use. Now, what does it give you then? So let's just run this code. So I had some noise here, and I'm trying to fit a second-order polynomial with a sixth-order polynomial, which is obviously not the best thing to do. But if you look at the result here, this is the one is the this k-fold is actually my handmade function, whereas the other one is what cross-val score from scikit-learn gives, and you see the results are the same. And in this case, you would say that, okay, for this lambda value here, this is the one which gives my best mean squared error. And that's the one I now want to use in the final training. So you would often use these models to fine-tune some of these hyperparameters. So in a certain sense, this is something which looks like a little bit like this hold-out method we discussed, except that hopefully the training and finding and tuning of these hyperparameters is going to be better than the hold-out method, where we just do this once. And we would have a train, validation, and test data. And where the validation part is used to find the best hyperparameter. Now, obviously, I have done 5 trainings here. And it means that in each training, there may be slightly different values of the parameter beta. Because at the end, the parameter beta is also something we want to provide to potential users of our model, right? So that means that what I do now, having fine-tuned lambda, I redo the training, and then I apply this at the final test set. So keep in mind, when you do the project, it's the final mean squared error on the test data, which is interesting. Another thing in the project, when you write the report, we are not interested in you running this for every complexity. We don't want to see all those plots. You can have them as supplemental material. So at the end, what you will provide is just one value of lambda for each complexity. And then for each value of lambda, you can do a final retraining. Okay? And for the functions you have first, you could actually generate new data for the final training set. So this is up to you. But the thing is that you use this method to fine-tune some of the parameters. And then having that, you do a final training. Now, this is obviously the sixth order polynomial is not very smart. So you can see that the results will also change if I now take away noise here. And if I now hit a second order polynomial as my guess, what you will see then is something which you might expect. And now you will see no noise, second order polynomial. I get a mean squared error which is close to zero. And in this particular case, ordinary least squares gives you the best result compared with ridge regression. But you see also that you have a plateau of values of lambda, this hyperparameter, where the mean squared error is basically flat. Yeah. Good. But we just need to take off these because I don't hear, yeah.
Something into this at least does.
Yeah.
And, yeah, what are just to say that MC or OS.
Yeah, yeah. So you don't know beforehand what you will get. And that is why many people, when they run machine learning codes, they would test several methods. So you could test the neural networks against the ridge regression, lasso regression, and then you would often pick the one which gives you the best results. Sometimes you have no sound argument for why that gives the best result, because you have so many parameters that it's difficult to develop an intuition. And in other cases, you can develop this intuition from the very beginning. So when you do a polynomial fit, it's often ordinary least squares which gives the best fit. When you have the topographical data, then this may not be the case. So in this particular case, you see what you expect to see, that when you increase the parameter lambda, then you're driving the parameters beta to zero, most of them. And at the end, the only thing you have when this curve flattens out on the top here, then in the mean squared error, you only have the data points, the outputs. And your model just gives zero prediction. And that's why this curve will flatten up at a high value, which is simply the sum of your outputs squared divided by the number of outputs. Because you have driven all the parameters beta to zero because you've been increasing lambda here. So when lambda is 10 to the 5, your model is essentially giving zeros in that case. So you can play around with this kind of simpler examples. If you add some noise, this picture may change. So if we do that, if we just rerun it with a second order polynomial, you may get something which still looks like that, but you see now the mean squared error has increased. If I again increase the order of the polynomial, I may get into a situation where, let's see if we just repeat it. You see now with a fourth order polynomial, we are now getting into a region where still the best mean squared error is for small values of lambda. And then something changes when lambda increases. So these are things you will expect to see. And you need simply to pick the value, like in this case with a sixth order polynomial, where the mean squared error is at its minimum. Now, when you do this kind of searches, what we did here was a kind of brute force by the eye search. So that means that if we go back to this sixth order polynomial, which we started with, so what you could do then is actually to stay roughly in the report that we see that the minimum occurs here roughly. You can obviously make a small interpolation among these data sets. And here I had an exaggerated number of lambdas. Normally you would just have a grid of much less results. Now, if you don't like the by the eye approach, there is another functionality. Actually, you'll be surprised, as I mentioned once, how many scientists actually do this by the eye approach. They just look at the graph and say, okay, this looks okay. But you have a function in scikit-learn, which is called grid search cross-validation. Then there is another one, which is called randomized search cross-validation. So let me just quickly say something about them. And the thing is that you will find, if you go into the textbook by Rashka, which I guess everybody has access to, you can find a nice discussion about these topics in chapter 6. And there are many code examples. Feel free to use these as long as you cite correctly. So if you're using examples from this textbook, or you take examples from the lecture notes, feel free to use everything you find, but we expect that you cite correctly, okay? So let me just bring up the textbook and just highlight those pages which are relevant for the project. So I should have this, let me see. Let me just bring it up again. It should be here. Sometimes it doesn't come up immediately. There we are. I didn't see the icon here. Too many windows. Now, in Rashka's textbook, as you can see here, there are several examples. So this is chapter 6. And in these pages in chapter 6, there's a good discussion of the implementation of K-cross validation. So just take a look at it. And as you can see here, there's also reference to a paper where they discuss the experiences people have gotten from using different sizes of folds. And in that paper, they typically recommend the number of folds you're going to use with a given number of data. So you can take a look at this paper here, and you can actually access this from the IP address of the university. And that gives you a more, how to say, practitioners in-depth, because this becomes a practical recipe. So it's not something which, how to say, you can show mathematically that you approach the correct mean squared error in the limit of large data sets, but it becomes, with a given number of folds and a given number of data, a practical recipe to get an estimate of the mean squared error and to tune the hyperparameter. So many of these recipes, like also the bootstrap, when Efron presented the bootstrap method, the proofs, the mathematical proofs of why it works, came after the method had been presented. And this is one of the nice things with machine learning. And this field, it's a novel field. And you will see in many cases that people actually just present something and it works by some magic. And then people try to understand why it works. So this algorithm we will discuss next week, Adam, which I mentioned has more than 200,000 citations. It's one of the most cited papers ever. This started actually by playing around with different parameters and finding a way to get an estimate of the gradients and the derivatives of the gradients. And Later, people came up with some mathematical justification, but many of these methods have been often presented with this ad hoc spirit. And that makes it quite interesting, because then it gives a lot of interesting meat for people who want to find a sounder mathematical justification. So in this specific case, if you move on a little bit, you will see an example of how you use it. So this is the same function which I showed you in that Jupyter notebook from the lectures this week. So you can see now the cross-validation score. So as I said, in the project, you won't get penalized if you just use this functionality, and we actually recommend it. But you can obviously write your own functions. And I mean, the group is so diverse that some of you actually end up writing your own function for cross-validation. But this is something which we leave to you to decide. This depends on what you like to do. You don't get penalized if you use these functionalities, but clearly you have to cite properly. So the elements of the code, you're going to put together functions from different sources. So you should cite the sources you've been using, but then clearly the way you put them together, that is your own intellectual work. And the idea is that you know what goes behind the curtains. So this k-fold validation, I hope you agree with me that the philosophy behind it is pretty simple. Any questions so far? I don't know if you agree with it, whether it's simple or not, but I think it's simple. Then, if you move on, there is quite some analysis on the bias variance relation, but it contains also a discussion on grid search for fine-tuning the parameters. So one function which you can replace this cross-validation score with is this grid search cross-validation. And as you can see here, this is the range of your lambda parameters, what you see here. And then you bring in that range, and then you have the algorithm, which could be ridge or lasso. You take the parameter grid, which you have here, and then in this case, you have 10 folds, and you perform a fit with that. And then it tries to find the optimal value in this span of values which you have given. So that's one way to automatize this by the eye search. Alternatively, and this depends on you, there is also the so-called randomized search, where you give a range of values and the function then, which is being used, so you give a parameter range, and the function which you would end up using is this randomized search cross-validation. So feel free to explore these options, but keep in mind that one of the main ideas here is to be able to fine-tune some of the parameters. And when you have fine-tuned these parameters, which will also depend on the number of folds, so typically you would stop when you see that the mean squared error doesn't change more than a certain amount when you increase or decrease the number of folds. So actually that result, which I showed you, will also depend on the number of folds I bring in. So if we go back to the, and just end here, we're going to end with that one. So let's just look back at this one. So if you look at this example here, if I now change the number of folds to, let's say, 10, let's see what happens then. That may change the result. And now it takes a little bit more time. And now you see that the curve is different. You see that? So you would have to play around with that as a new parameter, sadly. Next week, we're going to bring in 3 new parameters. Then the week after, even more. And this is just going to continue. So the hope, however, is that some of these parameters are those which are the most important ones. And actually, this hyperparameter lambda and the learning rate, which we use in the gradient descent methods, these are normally the parameters which are tuned first. because these tend to be the most important ones. And then the other ones become more sub-parameters, which we also need in the tuning, which can change the results. But as soon as we have stabilized on a value of lambda and the learning rate, we will discuss next week in more detail, then we would vary the other parameters. And these are often the most important ones. There's always some kind of disappointment when the number of parameters just starts increasing more and more. But I hope, again, that you can see the wood for the trees. And if you think of large language models with trillions of parameters, that's clearly a case which is, well, it's very difficult to extract, how to say, a deeper insight about the parameters. Okay? So we would find the best parameter lambda. And when we've done with that, since we have in this case 10 folds, we would actually have 10 different sets of the parameters beta. So that means that when we have this lambda value, then we make a new final training. And that's the kind of test data which you will present at the very end for each model. That means every complexity here. Any questions? Is it pretty clear? So the cross-validation is, you can view that as a way to fine-tune some of the parameters by getting a reliable or better estimate for the scores, the mean squared error. And then having nailed that one down, then you can do the final training on your data.